Hello and welcome everyone to yet another problem from Geeks for Geeks. This problem says root to leaf paths. The problem is quite simple, which means we are given a binary tree of nodes and we need to find the all possible paths from root node to all the leaf nodes of the binary tree. So here, starting from root 1, we have two leaves. So 1 to 2 is one path and 1 to 3 is a two path right from root to the leaves. So two leaves, two paths, and hence the output has this. So here 1, 2, 3, three leaves and three paths, which is 1, 10, 20, 40, 10, 20, 60, and 10, 30. Quite simple. And let's get into code. So from the problem itself, it's quite clear that we need to go within the depths. That is, we need to go from root to leaf, and that is which is meant by depth first search. So we'll just go ahead and quickly implement a depth first search traversal for this. Now it is clear that we need a depth first search traversal. Let's go ahead and create a DFS for this. So we'll take a root and another data structure. So what this data structure wants to be. So this data structure is nothing but it will keep a track of nodes which we have encountered so far. So 10 is the root, that's what encounter, 20 is the next, and next is 40. The moment we are done with iteration of 40 or the processing of 40, we go ahead, we pop the 40 as we have used it. So what is the perfect data structure for this? So yeah, without any doubt, it is a stack data structure, or more significantly, we can just go ahead and use a stack. So I'll create a stack first of all. So stack of integer, I'll say stack equal to new stack. So I've created a stack, currently it's empty, and ultimately this stack would create a result, the result of which is to be stored over here as a string. So let's build a string using string builder sb, or I'll say result is equal to new string builder. So this result would be storing the result, of course, result.toString. What more do we want? ToString. Now we need to go ahead and write the DFS algorithm. So I'll just go ahead and say static void DFS, and it takes first parameter as node root, second parameter as stack of course integers stack, and next is string builder. If I can write that, string builder res, and that's what it is. So yep, so first of all, let's check for validity. If root is null, we don't want anything to process, and we just will say return right from here. But in the case if root dot is leaf or is leaf root, we need to perform another logic. And what logic is that? We need to add a new line. So 40 was a new leaf, and hence we are sure that 40 was itself completed its path, and hence we add a new line character. So we just go ahead and append res dot add or append a new line, and we don't need to go ahead with this because we know it's a leaf and there is nothing forward to it. But when it's not a leaf node, so in that case we need to go ahead and we need to accumulate that within a stack. So stack dot push, what I'm going to push is the current root data. So current data, I'm pushing it, and then I want to call DFS again upon root.left with the same stack and the same result. But wait a second, we haven't updated the result yet. So result.add or append, or just wait for a while, we'll not update the result yet. We can do it later upon. As we have power of two data structures, we can anyway fill this data structure to this at any time. So I'll put stack and result. And of course, my friends, when this function or this root or this node scope would be end over here, at that time prior to this, we need to remove that from the stack as well. So 20 needs to be removed, so in order to accumulate 30. So we can take in that sense. But wait a minute, where are we populating result? So result is being populated only and only at leaf. So why bother filling it over here? So what I'll do is result dot fill, or I'll say fill result with stack. So it will fill result with stack in the proper fashion, not the default fashion of a stack, which is reverse order. So you know internally the stack is how the stack is implemented. Think for a while, maybe you can pause the video for a while and check how the stack is implemented within Java. So it will be a nice exercise for you. So I'll just say string builder res and stack of integer stack. So stack is implemented using a vector. Vector is very similar to array list, but it's a synchronized list. More on it we can discuss anytime later, but for a while you can assume that we can very well do this operation upon stacks as well. Size I++. We'll get stack.get I, and we'll get that element, and we'll just, instead of storing it, we can just on the fly go ahead and append it to result.append. And not to mention, we need to also store a space between them. Yep, that's how it is. Also we want an isLeaf method, so let's go ahead and use static boolean isLeaf. You know how to get a leaf or how to understand if the node is leaf or not. So we return the node is not equal to null, the first use case, and the node dot left is equal to null along with node dot right equals to null. So if left and right is null for a node which is not null in turn, then that is a leaf node. Let's compile this to check once. So it gave an error because we want list of list. So they made our life much more easier, as they don't want a string. And sorry, my bad, I didn't saw that they wanted not a string but list of list. So cool, if they wanted that, we'll provide them that. So we'll go ahead and say array list of array list, which is nothing but a result in this case of ours, is new array list, and that's what we want. So we'll be taking this final, as well, because we are not intended to change this anytime soon. Result, yep, and as this is list of list, I'm changing this over here as well. Yep, now it seems good. So now res is not a string builder, so we'll make appropriate changes over here, and in this case we just wanted to add stack directly, so we'll say new array list of stack. Pretty neat, simple. Stack.push, we are pushing the root, and that's all what we want, so we don't even need a fill method upon this, and result is being populated for everything. So let's compile this. So result.toString is still over here, I guess, so which we do not want, obviously, and let's compile it once. Oh, obviously, if it is stack.push, I wanted to have root.data here, so these two things are common, so let's cut this and let's take it above, and stack.pop in such case, and stack.pop in the rest of the cases where we are exiting. So remember, prior to exit we need to pop, that's the motto, and that's the real game over here. So we do not want context of one part to be shared within the other. So multiple errors today because we are not at semicolon, mostly compiler errors, I'm not sure, maybe due to IDE. So IDEs these days make a lot easier to program, especially during compiler errors and auto suggestions, but to the core it's all logic and you need to build that. So yeah, so we have completed the question, and here is what the result looks like. So yeah, this is how we have solved it, and obviously the time and space complexity is O of n and O of height of the tree, which is log n, and that too we are within the constraints, so not a big deal. Cool. So this was all about it. Do let me know about anything which comes up over here, and I'll see you in the next one.
Going up to the 16th floor, I just need a little more. Rocking out to Lorna Shore, making that thing swing back and forth. Look at us, we're out of sorts.